So welcome everyone to this meeting for this XR series. It is my distinct honor and pleasure to host Professor Fulvio Domini today. Fulvio and I have a bit of a history since we know each other. We've been knowing each other for about the better part of 14
years, I would say.
Yeah.
It's always the better part.
It's always the better part. And we made a promise not to age, and we're trying to stay at least inside of our head. We're committed to it. So Fulvio is a professor at Brown University in Rhode Island, United States. He got his master's and PhD in a lovely town of Trieste in the northeast of Italy. And then is currently is professor at the Brown University. Shall I call it Cognitive and Psychological Science Department now? Without the
we just switched, yes, CogSci.
Yeah. So I think Fulvio's work is fascinating. Is at the crossroad between what it means to see things in 3D and how to navigate space, and what kind of experience do humans have. And he's going to talk more about it in more detail. And also, how does this skill, help us manipulate rich objects, and with several applications, potentially and de facto for immersive technology, VR, and augmented reality. So, without further ado, I'll yield the stage to Fulvio, and grazie.
Prego. Is Italian okay, or should I switch to English? Well, thanks, Carlo. This is the first thing, like the mouse doesn't work, okay? Let's see. Okay. Thanks, Carlo. So thanks, Carlo, and everybody for inviting me to this. It's obviously a pleasure, and when Carlo invited me, he told me that there's a lot of interest about XR technology. And first I had to go online and check what XR technology is. Exactly, right? And XR technology, and I found this quote. I didn't I mean, it's nothing crazy important, but extended reality allows people to visit virtual environments and engage in experiences in an immersive, interactive way that can realistically is the bold thing here, match what they can access in the real world. And so I think that, I mean, when we see these goals of this technology, or all technologies want to create immersiveness, we have to ask two fundamental questions. First is, what is reality? And that is already something that I would like to say in this talk, but anyway, usually we consider reality as the physical reality which produces the signals that come to your eyes and they can use to interact with the environment. But the second question, I have to move this window somewhere. Okay. The second question is that apparently the XR system want to match reality, but the perceptual system, and that's what I want to talk in this talk, does not seem to match reality. So the question is, do we really need XR system to match reality, or we want something maybe different from this XR system, immersive system in general? So that's how I plug in my talk here. Okay. This is weird. Okay. Nothing. Okay. So since 1,000 years ago, from the time of Ibn Haytham, known to Europeans as Al-Hazen, we've been trying to figure out how a 2D visual input like this video produces the perceptual experience of a three-dimensional world. And the traditional way this problem is posed is this. Traditional question is, how does the brain infer the physical structure of the projected objects? In this talk, I question, and in many others, I question this formulation of the problem and ask if it really does it. And the traditional approach is based on the observation that is an infinite number of physical structures that produce the same retinal projection. Fortunately, not all interpretations of the image are equally probable. If you know how images are formed, you can calculate how likely it is that a certain object projects that image. And if you know what kind of 3D structure you can encounter more frequently in the world, then you can determine a prior probability. And so this is what you plug in what is called the Bayesian theorem. And you can multiply what you call likelihood here and prior and associate the probabilities to 3D interpretation, choose the most probable. So this is the kind of big idea here. And this is something that computer scientists can do for sure. But the question is, can the brain do that? And before we get there, let's see how this usually works. The image is decomposed into independent signals, often called cues. In this example, you consider two cues, disparity and texture. Binocular disparities are, as you may know, given by the different retinal projections that fall on your eyes. And texture information comes from the way that projected surface elements are systematically distorted on the image. Then it is thought that you have independent modules in your brain that calculate the probability of physical structure given the disparity cue and the probability of physical structures given the texture cue. So there are many, but they have different probabilities. Then estimates from these modules are combined in a statistically optimal fashion to get the overall probability of the physical structures given the image. And this estimate will be more reliable, like less noisy than the single cue estimates. Stop me, please, if you like. I mean, this is just to get the gist of the idea, right? But the brain tries to derive the most probable thing that projects on your eyes. The images are ambiguous. So that's the first premise here. Now, to have this premise, these models, they claim to estimate the physical structure, but we have to go more into the details. What do we mean by physical structure? And it really boils down to the relationships among measurements taken by a rigid stick. And these measurements will follow the specific rules of Euclidean geometry, the one you learn from elementary school, grammar school. I don't know how you call it here in the UK. I was going to say the United States of the Kingdom, but I guess it's the UK. Okay, so historically, the United States of the Kingdom. Yeah, that's true. Asking how the brain derives the physical structure of the cup you see there is really postulated that within the brain, there is a geometrical structure that obeys Euclidean geometry. And the mental rulers have exactly the same readout of the rulers of the physical world. The problem is that biological systems don't go around with rigid sticks to measure things and then see how these measurements are related to the images. Biological systems have wet stuff that transduces lights into electric energy, or soft stuff transforming mechanical pressure into electrical energy. And this is how the visual system is being bootstrapped to be successful in performing actions. So we have to start from this point of view. So, and here we go to the cave of Plato. Postulating that the brain can calculate how probable it is that a given physical structure can produce a certain texture pattern or a disparity field is a very big leap of faith, right? And also, even though Plato was not the one with the leap of faith, there was Kierkegaard or somebody else much later. But anyway, but this is exactly what the most popular theories of 3D perception assume, that the visual system has somehow associated sensory information to the Platonic structure that we call the physical structure. And the approach that I propose does not require leaving the cave. We can avoid being hurt by the horrible light of the sun, and instead can chill out in the cave and observe the relationships among the signals within the cave, okay? So without knowing anything about the Platonic world, we will notice the pattern of distortion of the textual elements and the retinal disparities, for example, they are related to each other. And since these image signals are computed through completely independent processes, we will conclude that the correlation must have some external cause, a common cause. In this example, I will call this common cause depth. So it is meaningful, this common cause, to the visual system because it also correlates with the hand grip that would successfully grasp the object. And okay, sorry. And so what I'm speculating here, and this is, we are at level of speculation, but those are the most interesting, the boring data, that the visual system has evolved to discover independent image signals that are meaningfully correlated. And this is how what we call latent variables describe these correlations are basically our access to the external reality. So of course, if signals are related to each other, the physical depth is this common cause, then they will also be related to the physical depth, right? So these two things are related to each other through physical depth, then therefore the signals are independently related to physical depth. But there's a catch here, though. Image signals do not only depend on these properties, but also on other factors. For instance, if you look at the cup from a large distance, the retinal disparities will become tiny. So the slope, what I call KD here, relating disparity in depth, vary with distance. And I will call this slope strength. So for now, you only have that sometimes the variable you get on your eyes is well related to the distal variable and sometimes badly related to the distal variable. It depends on the slope of this thing. And here the blue area is just a cartoonish way of indicating the range of possible strengths, okay? The strengths of texture will depend on the material property of the object and indicate this the range of texture strength with this variable KT. And therefore, distance and material compositions are these undesired factors that make these sources of information, as we may call them, unreliable to a certain extent. And the goal of the visual system is therefore to reduce as much as possible the influence of what we call these nuisance factors, okay? Please stop me if there's, if this is completely obscure or is slightly obscure. Okay, so this can be done by choosing a metric for this multi-dimensional space of signals that favor signals that vary less with what we call these nuisance factors. And you don't have to think about this equation. This is just a silly sum of squares under square root. That is a Pythagorean theorem, basically. But it can mathematically show that the length of the vector that has these signals as components will maximally correlate with meaningful variables such as depth relative to the nuisance variables such as distance and material composition. So, okay, so here in this very fast overview, we now go full circle from the ancient world of Euclid to the holy world of Bayes, who was, I think, a priest, and back to the Hellenic world of Pythagoras on the right side. So let's now directly compare very quickly the assumption and prediction of the Bayesian models and what we call the vector sum model, this very simple combination rule. And the first thing is Bayesian models assume that depth modules are noisy. This is another important thing in our field, that postulating noise in the visual system is a way that then you have a motivation in studying how things are combined. When they're combined, they're less noisy, okay? But the catch is that they're noisy but give you on average accurate estimate of the physical ground truth. And the vector sum model instead predicts generally biased estimates because it doesn't combine things to get you the veridical estimate, but critically does not depend on, does not predict these noisy estimates, predicts something deterministic. And I'll leave it like there. Bayesian model combines single Q estimate through a weighted average, and we don't have to go through how that's done, but the weights are inversely proportional to the variance of the noise. And the way, and this way, this achieves this statistical optimality. The AC theory signals are basically affected by what we think negligible or unimportant amount of noise, and doesn't depend on the particular Q. So it doesn't weigh signal. Instead, it produces this depth estimate, the increasing magnitude. So the more Qs you put, the larger is the magnitude of whatever depth estimate you're interested in. So now we're not going to go through all. We just give you one example of this last prediction, that the vector sum model does not predict a reduction of estimation noise, and instead combining Qs reduces the influence of these nuisance factors and increases the magnitude of depth. So this is work done by a PhD candidate in my lab, Jovan Kemp, who ran the studies where participants judged the depth of a sinusoidal corrugation, as you can see it here. This is just a cartoon. That's the display, if you can see. Can you see it, or sort of? Okay, imagine that that's a 3D corrugation. And these are the results in this condition. The dotted line here represents the veridical performance. And you can see that in this particular case, against what I've been telling you now, people were veridical in perceiving the textual elements. Now we have a second condition where only disparity information was available. Now how you can see on the left side, depth from disparity is actually overestimated at the 40 centimeter distance. This following many results that have been found already by Carlo years ago. And there's also a clear discrepancy between perceived depth from disparity and depth from texture. You see, one is larger than the other one. So there's a bias there. And but at 80 centimeters, you can see that depth from disparity is smaller. And this also shows you that there's a clear lack of depth constancy. So when something is close, it's perceived as deeper than when something is farther away. Now, all kind of the Bayesian models would predict that your perceived estimate should be in between these things, these estimates. And instead, what we find is that in both cases, the depth estimate is larger. Again, we have a combination rule given by a Pythagorean theorem. So the sum of the squares of the square root of sum of the square is going to be larger than each of the estimates. And here in gray, I show the prediction of the vector sum model. Is really important for this presentation, but you just plug in the equation, the perceived depth from the single Q condition, you get exactly that prediction. So when you combine signals, you have overestimation of depth. Okay, so this is one of the many studies we found this. And you can see this actually. Can you see it actually? So you should see the prediction of the vector sum model if you haven't got some of the aspects before, even in this case here. I mean, this is the worst viewing condition ever. This would be only shading, this would be only texture, and this is the combination of texture and shading. And you can see that the one on the left should be perceived as being deeper than each of the other two, even though the one on the left is actually the same as the other two. And so, the question is this. Now we want to have virtual environments that are where people can engage with something that is realistic, that matches the physical reality. But we have seen that this is not the case, at least for perceptual experiments. So how we are going to deal with this, right? Well, the first thing to ask actually is, these are real mistakes of the visual system, or maybe they're what we call cognitive mistakes, in the sense that the observers see something they really think they see deeper, but it's not really deeper. is basically some sort of response bias, okay? Are these errors really persevering in while we interact with the environment, when we perceive objects in the world? And well, you know, the best way to do it is to let people interact with objects. And for this, we have the 3D Information for Perception Action Lab, which was built by that guy on the left side there, basically, right? Started up in 2011. Yeah, actually, exactly, actually. As a system that is not your XR system you would see, you know, you buy in the store to play video games, but we have to be actually more precise in terms of resolution that systems that you are wearing for now. So we have a system where the observer looks through a mirror, an image reflecting from an old-fashioned CRT, because those are with the highest resolution, with stereo glasses, and interact with the environment. Of course, here this light, otherwise you can see the video, but the light is turned off, and you just see this virtual reality world in front of you, and you grasp objects. And you can also have some sort of haptic feedback given by these objects. So we can play also with haptic feedback, and the experiment I show you now will make sense. And this is, you know, one of the tasks that have been used, this front-to-back grasp. This was actually from a paper that Carlo published a few years ago. So a graduate student in my lab, Chen Lim, asked the question, is 3D vision for action getting a grasp on reality? In the sense, how can we know really that the visual system is making mistakes, having errors, or is something that is bias introduced by experimenters? And the only way to do it is to ask the visual system itself and let the visual system judge if there is an error or not. And in a second, I'll tell you what I mean. Again, this is another demo that I showed you before. These are all spheres that depict exactly the same depth. But as you can see, as you add cues, you have the impression that they are deeper. So, how can we achieve a succession of action if our perception is not accurate? So that's the first question we want to ask, because it's kind of a paradox. So, and to explain this paradox between perception and action, some researchers have proposed that instead of having one visual system, we have two visual systems. One visual system is a system for perception that gives rise to all these perception illusions and these distortions. And one visual system is the one that gives you the ground truth. Okay, so we can go back to the Bayesian approach, say, well, maybe it is true that we have access to the ground truth. So now we tried to test this, and to test this, we took advantage of a specific mechanism that happens when you make an error, right? When there's a misalignment between your perception and your action. So let's suppose that this texture bump you see there, can you see a texture bump? Okay. As some true, gives rise to the true perceived depth. And for now, I'll use D here for true physical depth and D hat for the perceived depth. So let's say that D hat is equal to the true depth. If I add shading to this bump, I see more depth. Okay, and this is this depth overestimation that you can see there in the purple or red thing. However, because vision action can provide veridical estimates, if that's true, our grasping is not overestimated and always correspond to the true depth, and that can be the reason why perception is accurate. So this is the two visual stream theory assumption. However, it is never, one of the things we have to ask is like, do we really need to pause the existence of two visual streams instead of one visual stream? And so if we extend the IC model for vision for action planning, we can explain accurate action with a single visual stream. So let's look at the bump again. If perception and action rely on the same visual stream, then action will be planned based on the perceived depth. So in that case, it means that both our perception and action are overestimated. So you go and you grasp the object with a larger grip aperture. Then how we can plan an action accurately? So what is important here to know that perception and action have a different unit of measurement, right? Action has all this system of motor control. You can think about it, distill it as something composed of a perceptual thing and plus this internal state that as much as you adjust the grasp of your hand. So if you have the texture plus shading stimulus, you go and grasp it larger, so your internal state has a certain value. But then when you get there, you receive a feedback. And this feedback is telling you, look, your grasp was too large, right? Because maybe, the forces you experience are smaller than you would have experienced. And vice versa, if you grasp something that you think is small and is bigger, then you get forces that are larger, okay? So this is something automatic then that says, okay, it's too large. Then you can simply reduce this internal state, okay? To reduce the planned grip. In that way, even though the perception is still faulty, the planned grip will correspond to the true depth. And so, and on and on. Now we go one step further. Now we give you back. So this is what we call phenomenal visual motor adaptation. I don't know if you have ever seen a prism adaptation or you have been taught about prism adaptation. If you shift the whole scene to the left, for example, and ask you go and aim at this point here. The point is actually here, and you see that your finger is displaced, and then you very quickly you adapt to this displacement. There's nothing smart that the brain does; it just moves the muscles in a way that corresponds to the to get you successful. Okay, so but then there's a phenomenon we call an after effect. Because if I give you again the same stimulus as before, the texture stimulus you had before, now your hand is grasping things smaller, right? And since this looks smaller than that, you're going to grasp it smaller. So you have this after effect and you have to readapt again. Okay, so what is the bottom line here? The bottom line here is that this kind of technique to see if the visual system is affected by this sensory motor adaptation, this technique is something that can allow you to determine whether the biases that we see in perception really exist in action, because it's the visual motor system that is detecting these errors and reacting to the errors. So we are not doing anything as experimenters. We let basically the visual system is experimenting itself on whatever stimulus they have. And of course, to do this, we have to use the system that Carlo built with other things added to it, but not that many. So the idea here is that, again, remember, you can have grasp your objects, but you can also feel them. So we can deliver the haptic feedback. Okay. So I'm good at time. I'm 26 minutes on my clock here. So just ask me question if you have any questions in between. So, okay. So let me go through now. It's awkward because that is there and this is here, but go through the predictions of if it's really true that the biases we see are there. So we start with what we call a single cue condition. You have a bump. Again, erase what I told you so far with texture and shading because it's the only way I could present it on the monitor here. But we had disparate information and textual information. Okay, so we consider these two things here. Disparate information is, can be represented only but with random dots. In our case, we'll have what we call uninformative text. So disparity signal only. Okay, this is the single key condition. We assume that this thing is perceived veridically, which is an assumption that is wrong. I tell you now, but it doesn't matter for this reason. Okay, so you have a baseline condition where you grasp a single Q condition. Basically, whatever the prediction is going to be everything. All the models predict that you're doing the right thing. Now, the multi-Q condition, the IC model, the vector sum model that I told you about, is going to tell you, okay, when I give you stereo plus something else, plus texture, you're going to see more depth. So you have a jump here of your perceived depth of the stimulus. And overestimation, as I said before. So if that's true and the visual system feels that, the visual motor system, then it should adapt. Even though, again, in these experiments, these effects are small enough that nobody notices. All the subjects don't notice that there's something weird going on. They just do the task. And probably you're doing it all the time in the real world. So if we repeatedly touch the object, then we receive haptic feedback telling the true depth, and therefore we have this visual motor adaptation. Then I go back and give you again the display before, right, the single Q condition. And in that case, what happens is that, well, you should have what we call this after effect. So you should grasp smaller, because here you adapted your motor system to say, oh, things are too big. So I have to go smaller. And then all of a sudden you're smaller and you have to go back up, okay? And then we did a trick at the end. We represented the multi-Q condition, but now we created something that for other models would be a conflict. We took the multi-Q stimulus, the stereo plus texture stimuli, and we pushed it so that this is perceived as a single Q. Because remember, when you put the two things together, you have more depth, perceived more depth, okay? So here in the multi-Q condition, you perceive as much as the single Q condition. So you have a condition in which the physical depth is smaller, but the perceived depth is the same. And the physical depth is actually different from the haptic feedback. So this is really kind of a control conditions, like what if you do things that one model perceives as being an error and the other model doesn't? And we predict that nothing happens because there is no change in perception between this condition and this condition. So Cheney, first of all, did, and well, this would be the prediction of the other models instead. The other model would say, well, when you go grasp this, you're grasping too small because it's, this is what the visual information is giving you, but the haptic feedback is bigger, so you have to go back up. So that's that would be the two sets of predictions. So before jumping into this, let me go through this how we collected this, created this multi-Q condition here. Subject were doing this perceptual matching task. We project the stereo image to the mirror, so the reflective virtual stimulus will appear on the monitor and therefore behind the mirror. And so participants, so this is the single Q disparity only. This is the texture information that is null. Here you wouldn't see any bump. Of course, I cannot show you the disparity stimulus. I would have to have stereo glasses. And then you have the disparity shaping stimulus, which is the multi-Q stimulus. And this is the actual shape shown in rotation just for illustration. So you have to adjust the depth of the multi-Q stimulus. So you have to push it. And the way you do it, you say, okay, so I give you a single Q depth, and then I give you a multi-Q depth, and you have to adjust it so the two match. And for doing that, you have to reduce the depth of the multi-Q stimulus so that the adjusted depth is perceived as the single Q depth. Okay, we did this and we found exactly this, that if this is the single Q depth, this is the adjusted, this is the veridical line, everything has to be pushed back, so made smaller. Now we're ready to do the grasping task. Again, people were seeing this thing through the mirror, and they were receiving actually haptic feedback with actual printed shapes that corresponded to the what we were interested. And we measure what is called the maximum grip aperture. Is basically the grip aperture you have when you grasp an object, and then you have to close over the object. And maximum grip aperture has been shown to be related to the actual perceived depth of the object. Again, these are the predictions. Before we go, at the beginning, you may have something veridical, then you have an overestimation, visual motor adaptation, you have an after effect, you go back up, and then you stay there with the multi-Q stimulus that we have created so that it looks like the single Q stimulus. And the results show exactly this prediction, okay? However, we found also all the results we found in the past with Carlo studies where disparity stimuli are also overestimated. So you start already with an error, you adapt to the error, then you add information after you had the error, and you have an error again, and then you adapt to the error just with the motor system, and then you have an after effect. And then when there is actually an error in the world, then you're straight there. There's no change. Yes.
On the first bit, they start with an adjustment. What is this? Is it the that what's happening?
Oh, the adjustment. Oh, I'm sorry. In the perceptual task.
Yeah. So so you have on the first bit the same Q.
Here.
You just mentioned that.
They don't do anything. They just see this thing, then go and grasp it. Nothing else. Okay. So do many grasps, and then we go to the second block, the third block, and the fourth block.
Each grasp they are getting.
Yes. So these are single trials, and these are the trial numbers on the x-axis. Okay. Sorry about that. Yes.
Why for the last one an error, not an error in the reality?
An error in reality because the haptic feedback here is different from what we render. We render a depth that is smaller.
Why is not an error also?
The first multi-Q, we are not, this is not an error because we just add Qs to the same depth. It's like you have either only disparity or disparity plus texture, but the depth of the physical structure is exactly the same. They're not different. So there's no error here. There's a perceptual error.
Okay.
But here there's an error, like formally an error.
So first one, the blue is the size of the object.
Yes.
But I give you the impression it is more, there is more depth, right?
You're talking about this?
The second one.
Yeah, the second one, yes. So the second one, yeah, let's say this is the actual size of the object, but this is what you perceive. You see more depth. You see more depth. Yes. You perceive more depth, but the actual depth is the same.
Okay.
I mean, Carlo did this years ago even with a real object. It was a cardboard that was either static or rotating, and when it was rotating, people were grasping with a larger grasp. So it's a pretty robust effect, even with just cardboards. Not because you never know with the monitor. Maybe there's some problems there and stuff like that, but this is pretty much confirmed.
It works the same with the percent.
Yes.
Do people notice that you switch from single Q?
Well, they see. I mean, obviously something changes.
Yeah, but because as you show it now, from the third to the fourth, maybe they wouldn't, right? So if you change from a single Q to multi Q, that like evokes the same depth.
Yes, they wouldn't.
So then it wouldn't be as surprising maybe if the grip doesn't change. Right? They don't perceive like they change.
I mean, for sure, from single queue to multi-queue here, they see there's a change, but they stay the same. It's a good point. Yeah. But the important thing here is also this is our predicted distortions, right? So we predict them. Yes.
Maybe I'm getting, but
No. Go ahead.
would this essentially show that if you just start with the last one to the multi-queue perceptual identical, would people be more accurate?
If you switch the multi-queue with the multi-queue, this one,
I mean,
and you put it here,
you just start the experiment with the last condition.
Oh, with the last condition. We don't know. It's a good question because we have no clue, basically. So we don't know where things are right or wrong. So with stereo information, we found, for example, that apparently, and this is really like a long studies that we did years ago, is that it seems that when objects are too close and you have disparate information, you see them too deep. When they're farther away, you see them squeezed.
Yeah.
But there is a distance, which is suspiciously the one where you grasp and manipulate objects where things are correct. So we think there is some sort of calibration around the sweet spot there. And but this is all, unknown terrain. We cannot predict anything absolute, only relative, basically, what happens. Okay, so I guess, there's not much more to say about this. Let me rush through. Let's see if I can do in 10 minutes this one. So then we asked, and maybe I'll skip a couple of slides, but maybe all these displays are static objects. You have to grasp them. It's a little bit unnatural and does not really reproduce the physical world. XR systems reproduce the physical world. You have things that fall down and so on. So at least is our visual system incorporating knowledge about physics. And so let me see if I can rush through this. I'm not interested in situations like this one. So this is because here, when you have to grasp a baseball, for example, you just have to, there are some heuristics that don't require your knowledge about where the ball is. You just have to keep, in this case, what is called the bearing angle constant, right? And then you grasp the ball. So this, maybe baseball players use this. Since I'm Italian, I'm more interested in situations like this. I hope nobody gets offended here, but where you have to kick a ball and the goalkeeper has to catch it and measure all the visual information. Anyway, unfortunately, the experiments we do in the lab are not as fun and sexy as playing soccer, but this is a situation where in this kind of experiments, you have a ball falling towards an observer, and the subject has to simply judge where the ball fell. Again, we have this rendering with the system, this pretty high resolution. This is a very fast fall, okay? All right, so can we do that at least, when you have something that is more naturalistic? There are two main kind of sources of information with which you can do this task correctly. One is the verges of your eye can tell you where the final point of the fall of the ball is. So that's already enough for solving the task. You can ignore even the falling of the ball, right? But of course, these are very fast movements. And another information can be the predicting information about the ball approaching you, right? With this, whatever, velocity BC that I wrote there. Okay, so you have these two things at the same time. So can we do this? The information you get from the ball falling and the velocity is very important and has been known for many centuries now, since Galileo Galilei. Not to show off some other Italian guy here, but you know from the initial velocity of the ball what the trajectory will be of the ball. So it's possible that the visual system has internalized this kind of knowledge. So the subject was seeing this ball falling, and the ball could fall in 6 possible locations on the ground. Okay, and we manipulated in a very funny way the visual information. So we created 3 kinds of gravities. We created a Mercury gravity where the ball would fall slowly, right, with the 3.7 meters per second square. Or we created a Jupiter gravity where the ball could fall faster, or at Earth gravity. Okay, and to keep exactly the same trajectory on the screen that they were seeing, so that we could compare these conditions, we modified the velocity so that on Mercury the initial velocity was slower, and on Jupiter was faster. In this way, you are guaranteed that the ball falls exactly along the same trajectory with different dynamics. So now, what are the predicted trajectories? Well, if the visual system incorporates knowledge about Earth gravity, it would say, well, in the Mercury condition, I see the ball falling faster than what you displayed, because I assume that the fall appears on Earth. And therefore, the ball should be underestimated, in a sense, should be falling closer to the edge than it is in reality. And the same thing is, if the ball is falling on Jupiter, then it should fall slower than what I display, because now Earth gravity is smaller than Jupiter, okay? And therefore, the ball should be seen as being closer to the observers. So in other way, if you plot the display position in Z and the response in Z, then you should have the Mercury should be falling closer to the edge, so underestimated, in Jupiter farther from the edge, so overestimated. And these are the results we get. Okay. So now is 45 minutes. So I won't go through the other slides of this experiment. But one thing I can tell you, so this is nothing to do, maybe I can do 1 or 2 slides. Somebody could say, well, yeah, look, Fulvio, you are telling us that you modified initial speeds so that, on Jupiter, you have to have initial speed that is larger, and on Mercury, the initial speed that is slower. Maybe that's the manipulation that created these biases, is not embedding the hypothesis that is falling on Earth. And to do the sanity check, we did the opposite. So we had the ball now falling up instead of falling down. In that case, you shouldn't be any possible prediction based on this, because you cannot predict anything if it's falling up. And in fact, in that condition, we basically found no difference between the Mercury and the Jupiter condition. So when we turn the thing upside down, this wouldn't work. I won't go through the rest. I'm just telling you that while I'm going to the rest. But when we said, okay, what happens when you have a static ball just flashing in those positions and not the ball falling down, then you have basically correct estimates of where the ball fell, right? So you saw the data. The data show you that there's an overall overestimation. And you remember the vector sum model that I showed you before. There's something that pushes things up a little bit, right? But the bottom line, what seems paradoxical here is that it looks like there is veridical perception when you have static information. When you add the velocities and you add more information, you get these biases. Okay, so even in this case where we think, and I won't go through the slides that explain to you that, but we think that really the results can be explained by the fact that you incorporate knowledge about falling objects on Earth, which makes sense. Even in that case, that doesn't lead to more veridical information. So we have to ask ourselves whether we could maybe design systems that are taking this into consideration and facilitating things. And I have no idea how this can be done, basically. But I would say I had some sort of conclusion slide, but I think we can stop here. Thank you very much. This is the our lab, a couple of generations later. So. Do we have any questions? Yes.
I have 2-3 questions.
You know, start with the first.
Okay. Some are more methodological. I'm not an expert in your field, so maybe you say maybe they are basic questions, or maybe you have addressed them in other papers, or some others have addressed. And some are more theoretical, and what are the implications of the work. So a methodological question: the object behind the mirror always remains the same between trials?
It depends on what experiments
In the experiment that they've shown.
So in the one with Cheney, on purpose, we kept exactly the same object.
Even with the one that you have the other.
It's always the same object. Yeah.
Okay. And in the paper, in that work, you discussed that if there is sort of error in the reality, so the fourth last condition, there is no adaptation. But those the assessment of those errors rely on 2 different senses. One is tactile and one is visual, between the second and the fourth condition. So the question is it possible that for sure there are different sensitivities with the visual system and the tactile system to consider a difference, and a real difference, or a difference that must be taken into consideration. So maybe the absence of adaptation is just because the visual system was more sensitive to the depth that you created compared to the fourth condition. So maybe if you have made the object flatter, okay, more flat.
So let me unpack 1 second. Yeah. So the first thing is, and in this process of sensory motor adaptation, what we think, or I think what is thought that is happening, is that you plan an action. You don't measure anything really with your fingers or with your proprioception. I don't think that's actually the case at all. You just plan the action, and when you plan the action, you predict some forces that should impinge on your fingers when you go and grasp the object, right? And these forces are off, are too big or too small, then the motor, just the motor part of it, adjusts a little bit to correct for that. So when I look at these things, unless there's some weird, then, well, this is getting, often it kind of worms, thinking about if you have like perceptual learning. But in this very simple case, I think the only driving factor is what you perceive, the depth you have. And the depth is always wrong in this case. What changes is just the grasp, because you experience that force that is too big or too small. And this is completely unconscious also, like this is a few millimeters. I don't know if you saw that, the subjects don't know anything about it. So I don't know if it answers your question, but that's the...
In part, but maybe later. So then the last part that is related to another question is, so you started about Bayesian versus Euclidean. So in the end, even the last study,
no Bayesian versus Euclidean.
or whether or not there is some Bayesian, Bayesian integration or Euclidean system in the brain. And so one point is, what if the brain uses both, but in different situations? That is, all your studies, if I'm not wrong, have shown, especially the one of the grasping, have shown the stimulus that occurs, and the stimulus remain the same also during the grasping. Okay? And you always talk about the visual system, the perceptual abilities, the visual perceptual abilities. However, if I am a participant, I can quickly learn, and as soon as I see an object, I plan an action. This is a top-down influence. Okay, a top-down motor program that they have to implement. So the question is, what if it is truly a visual effect, what you see, what happens if when the person started to grasp, you add some visual texture information that changes the depth. So the motor program has been already planned, but
That's a good question.
in the middle of the action, you change the visual information. There, I think we can talk about bottom-up. A purely perceptual visual influence. Otherwise, as soon as I see an object, I plan it. I've learned that more or less I will have to do some movement, and this is a top-down influence. So frontal information that allows me to.
Maybe I don't know. Like I'm not really. I never got to the frontal part of the business here, but you may make a decision about grasping something, right? But the information that drives the actual planning, the motion, the motor planning is, I would say, in most of these cases, it's bottom up, right? I mean, you have disparate information, it's instantaneous. You go and you grasp it. I don't.
There are also memory information.
No. I don't disagree with you in general that you use all these things, but to predict these results, you don't need to make any assumptions about what your kind of belief about the world is. I mean, I mean, this is more of like a large beer discussion.
Well, but I think that if you change the visual information while the action is ongoing.
No, that's a great idea. That's a good idea.
The same effects, I think, is much more strong to say it's highly visual and less frontal, temporal, memory based, shape based. Just
yeah. No. I mean, it's a good question. I mean, yeah.
I have a quick comment / question. Fascinating stuff. My interest in this is someone working in VR, AR. There's a lot of talk about, proper depth perception in lots of different situations. My question is, do you have time to talk about this today after? Or are you busy the rest of the day?
Talk about.
Are you busy the rest of the day?
If I'm busy, that's the question. I'm not. I'm not. No, I'm cool. Yeah, no, I'm not busy. We can talk about it. Yeah. That's the easy one. Okay, thank you.
Awkward.